OH. One more time. OH. Welcome, everyone. I'm really pleased that I get to fill in for our dean this year. I'm usually in the audience, but this time I get to give a little bit of the history of this particularly really great series. Lima is the hometown to one of the world's most famous astrophysicists, William A. Fowler, who won the Nobel Prize in Physics in 1983 for his efforts to show how all the natural elements in the periodic table are forged under extreme conditions across the course of a star's lifetime. William Fowler was raised in Lima, attended Horace Mann Elementary, and graduated from Lima Central High School in 1929. He earned his Bachelor of Science degree in engineering physics from The Ohio State University in 1933. To honor his achievements in astrophysics, Stardust, the William Fowler Science Series, was born through a partnership between the City of Lima, Lima City Schools, and The Ohio State University at Lima. The William Fowler Science Series is a cross-disciplinary program for the community and local middle and high school students. The Lima City Schools, in collaboration with outstanding Ohio State faculty and leaders, focus a portion of their fall semester science curriculum on the Science Series topics of the year. More than 80 high school and middle school students will be on campus learning in our labs. This year marks the 11th year anniversary of the Fowler Science Series. I've been here the whole time, and it doesn't seem like it's been 11 years already. It's just amazing. The most recent topics and speakers have included Dr. Wayne Schlingman, Why Eclipse Enthralls Us, Dr. Aaron Wilson, Our Fascination with Weather and Climate, and Dr. Bart Elmore, environmental historian, explores the growth of Coca-Cola by tracing its ingredients. Now I'd like to welcome Lima Mayor Sharita Smith to the podium. Welcome.
Thank you so much. Good morning, everybody. I know it's already been said, but I want to do it one more time. OH. Awesome, good. So it's been said, I am Mayor Sharita Smith, and I am happy to continue this tradition and partnership between the City of Lima, Lima City Schools, and The Ohio State University to bring the William Fowler Series to this campus. It's a great honor to be able to speak to so many brilliant young minds today. And I'm going to start out by asking you guys a question. You listening? Yeah. All right. Have you ever heard the well-known proverb that water is more valuable than gold? You ever heard that? Awesome, good. Raise your hand. Awesome. Tell me what you think that proverb is about. No wrong answer. You want to take a stab at it? Yes, ma'am. Sir.
That water is more valuable
That water is more value for life as compared to gold, because gold just brings monetary value. I think that's a really good answer. Thank you for that. That's right. Water is incredibly important, whether it is about keeping our bodies healthy and hydrated, growing our crops, or raising our livestock, or also generating sustainable power. Water is essential. It's a universal resource for all living organisms. Despite this fact, the amount of readily accessible fresh water is becoming increasingly scarce due to outside factors like population growth and climate change. Although the Earth's surface is made up of 71% of water, only about 1.2% of the water is considered really drinkable. Because drinkable water is such a valuable resource, it is important for us to all do our part in preserving and protecting what is left of it. Cultivating water consciousness is one way that we can all do our part. Minor changes to everyday life, like turning off the faucet while brushing your teeth or only running the dishwasher when it's full, can also make an impactful difference over time. So, if you only remember one thing from my time with you here today, remember that water is valuable. So say it with me, water is awesome. By educating ourselves, we can all do our part to create positive change. We are excited to have Dr. Christopher Winslow, Director of the Ohio Sea Grant and Stone Laboratory at The Ohio State University, here today as we learn more about the importance of our watershed in our Great Lakes. But before we welcome up Dr. Christopher Winslow, I want to thank everyone that made this event possible for today. Looking out in the audience, I see a room full of people invested in the future of our next generation. The partnership between the City of Lima, Lima City Schools, The Ohio State University is a great example of how collaboration can enhance our educational impacts throughout the community. I also want to thank my predecessor, Mayor David Berger, who's also here, for his vision and leadership in bringing this series to our young people. Thank you all for your ongoing work. And in conclusion, I will invite up Jill Ackerman, Superintendent of Lima City Schools.
All right, good morning. I'm happy to see you out here. So we want to give a huge thank you to the Dean, Dr. Margaret Young, the Ohio State University, our Mayor, Sharita Smith, and the City of Lima for this amazing partnership. And as she said, we would not be here today if it had not been for the vision of our former mayor, Mayor Dave Berger, who so many years ago had a vision for this series that brought us all together, and here we still are. I also want to thank the planning committee. So there were people behind the scenes that did all the work to make the day happen. That is Mr. Steinmetz and Mr. Fallis, Mr. Albright from OSU, Mrs. Kristen Lee, and Ms. Jokinen, who is running around here taking photos. Now today, by learning about Lake Erie, you're not just getting knowledge about a natural wonder, you're also understanding how important that it is and how it serves all of us. Small actions like keeping water clean, reducing pollution, can have a big impact. As future leaders, you can help protect our amazing Lake Erie for generations to come. So dive in today, because Dr. Winslow is going to give you some great information. From what you hear today, I'm sure that you will be able to appreciate our lake even more and take part in preserving it for the future. So we're going to give him our best attention, right? Because you're all going to pass my test when it's over. At this time, I'm going to ask Mr. Albright to come forward. Thank you.
Okay, to get things started, I get to introduce our keynote speaker. Dr. Winslow is the director of both the Ohio Sea Grant Program and the Ohio State University's Stone Laboratory, OSU's Island campus on Lake Erie. The shared mission of these two programs is to sustain and enhance the vitality, value, and wise use of Lake Erie and its watershed resources. Ohio Sea Grant is one of 34 coastal-based programs across the country and reports up to NOAA, the National Oceanic and Atmospheric Administration. These two programs help the university's academics, agencies, and coastal partners to 1, address the habitats and nutrient loss, 2, assess the impacts of climate change on the Great Lakes, 3, support sustainable fisheries and aqua life, 4, understand and combat invasive species, 5, build clean and safe marinas, 6, support coastal business retention and expansion, 7, address microplastics and marine debris, and 8, understand the impacts of emerging contaminants such as pharmaceuticals and personal care products. Prior to Dr. Winslow's current appointment, he received his bachelor's degree in biological science from Ohio University and earned his master's and doctorate degree from Bowling Green State University. Chris, his wife, and 2 children live in Clintonville, a neighborhood of Columbus, Ohio. Please welcome Dr. Chris Winslow to the stage.
I wander when I talk, so I'm going to take this off and walk around. Who loves science? Raise your hand. All right, good. Every one of you, I want you coming for my job because I got to retire sometime. Need your help, okay? So we're going to walk through harmful algal blooms and nutrients. So HABs, H-A-B is harmful algal blooms, and I'm going to walk you through this thing. But I also, when I give talks like this, I am curious what's going on in your brains out there, and so I'm hoping you're going to have questions for me at the end, but I also hope that you ask questions that aren't related to this topic, because Lake Erie is a resource for all of us. And I love the mayor's words, right? That water is important. It's very valuable to us, more valuable than gold. Okay, so let's hop into here. First thing is I don't do science just for science sake. I am a science nerd. I love running experiments. You heard I have a bunch of degrees from universities. I'm a science guy. But this is what matters to me, folks. Let me see if I can get this to progress forward. 1 second, folks. We can do this piece of cake. This is why, folks. My job, in my opinion, is to do science to help you behave on the landscape. Okay, if I just do science and write a journal article about it and put it in some library, it doesn't make a difference in the world that we live in. And so what I need to do is when I leave this room, I need to hope that you guys are going to take what I've told you and do something in your own backyard to protect that precious water that we all interact with. So what can you do in your backyard and at home to address that? So that's one step. The other thing that means accomplishment in my job is to inform management decisions. This picture up here has a bunch of federal employees. This is the director of your Department of Natural Resources and your governor of Ohio. These folks make decisions on how to protect the land, protect water, protect our wetlands. And so the research that we try and do at Ohio State University and the job that I have is to give them science so that they can make great decisions. So we're not just doing science for science sake, we're trying to inform the way that our agencies behave on the landscape. And the golden prize for me is this last one. The science that I do is targeted to inform policy decisions. This is federal Congressman Bob Latta from the Bowling Green area of our state. We need to make sure that the science gets into these decision makers' hands so that when they pass laws and regulations, they're doing so to protect the environment rooted in science. So those of you that raised your hand out there say you love science, you can do more than just an experiment. You can use that science to change behaviors, to inform the way our agencies manage the landscape, and you can even inform federal regulations and state regulations. So I empower you to take that science that you love and do something with it. Lake Erie, it's beautiful. I know it's a bit away from you. It's quite a drive, but these are a couple of our beaches outside of Cleveland, Edgewater and Huntington. This is the Cuyahoga River that runs downtown. This is Cleveland at night. Beautiful, beautiful place. Place that many people love, enjoy, recreate on, drink water from. Beautiful place. But sadly, I've got to tell you that Lake Erie is also a case study. And what case study means is we've learned lessons from studying through science this beautiful lake. And this is what I mean. This is the Cuyahoga River from the 1970s. That is fire on top of water. Okay, that typically tells you the environment's not very healthy when water catches on fire. And so this happened in the 1969. Actually, this was the 12th time that the river had actually caught on fire. And this is the shipping and industry that happened in downtown Cleveland in the 50s, 60s, and early 70s. We destroyed this environment. We were actually mentioned in a book that you've probably heard of or seen a movie called The Lorax. And I'll read it for you if you can't see it from where you're sitting. But it says, "You're glumping the pond where the humming fish hummed. No more can they hum, for their gills are all gummed. So I'm sending them off, oh, their future is dreary. They'll walk on their fins and get woefully weary, in search of some water that isn't so smeary. I hear things are just as bad in Lake Erie." The first edition of the Lorax's book called out Lake Erie for being this horrible, polluted, and disgusting place. But what I'm here to tell you is that good things have happened from that disaster. So in the 1970s, the Environmental Protection Agency was created, the Clean Water Act was created, and the Great Lakes Water Quality Agreement. All three of these things happened in 1970 because of those fires in 1969. And on the backside of that, in 1972, just 2 years later than that, Earth Day was created. So what I want to show you is we have a period in our history in this country of pollution, and nasty pollution, water catching on fire kind of pollution. But the science and the people that live in that community have started to turn the corner. And so I'm going to talk to you about some of those successes, but we also have to talk about this harmful algal bloom issue that we're facing right now. Okay? So there are still some persistent and novel things that we need to address. So this is it. If you haven't driven up to Lake Erie or been on the water, this is what it looks like in the summer. Bright, bright green color. Okay? And basically this is because we have too many nutrients. Does anybody know what that N stands for as far as nutrients? Nitrogen, absolutely. What's the P stand for? Phosphorus. Great. Smart people. I love it. Thank you. And thanks for raising your hand when the mayor asked about water. Brave to raise a hand. Congratulations. Good work. Impressed. So this is what it looks like. You can even see the trail from this Canada goose swimming through the water. Don't call them Canadian geese. They hate it. It's a Canada goose. That's them. This is a colleague of mine holding a glass of water. And here's a net trying to pull water from that lake. Even more dramatic, in my opinion, this is a friend of mine and his family on a boat on Lake Erie. That's not normal. That's not healthy. And so we know this issue is there, and what we're trying to do through our science is figure out a way to solve this problem. I'm going to show you some data, okay? Don't get scared. I saw hands raised. You love science. I will walk you through each one of these graphs for you, okay? So we said this is caused by nitrogen, N, and phosphorus, the P, okay? But those two nutrients are on the land. So how do we get them from the land into our rivers and then ultimately into Lake Erie is because of rainfall. Okay, those N and P, the nitrogen and phosphorus, wouldn't cause harmful algal blooms if they just stayed put on the landscape. But here's what we're seeing. This red line right here, where it's labeled 0, that is the average amount of precipitation from 1951 until 1980. So they take how much rain fell in this Great Lakes region from 51 to 80. They take that, whatever that number is, they make it 0. And then they go back through time, since the 1900s, all the way to roughly present day, and they put a dot for the actual rain in that year. So what we're trying to do is map the actual rain against this average. So anytime these dots are above that red line, it means it was a wet year. And anytime they were below, it means it was a dry year. This blue line shows the average through time. And what you can see, since the 70s-ish, we have been well above that line through time, and you can see it's climbing even more dramatically. In the Great Lakes, we are seeing 11% more rain than we have through time, through historic time. So what we have is not only nutrients on our fields that's causing a problem, we have more rain to carry those nutrients from the field into our rivers. And so this is what we as scientists are looking at, is how do we stop the nutrients from being applied in the first place onto our fields, and how do we stop them from leaving? And that's what I'm going to talk to you about today. Here's just to show you what this precipitation looks like. This is one of our science vessels up at the lake, and I hope we can find an arrangement to get these classes that are sitting out here up to the island. But these are the two windows and the door of that research vessel in the 60s. So you can see it's well below the dock. This is that same vessel. Those are those two windows. There's the door. In 2014, you can see the whole cab of that boat on that dock. This is 2019. The water is now up on that dock, and the boat is probably 6 feet above where it was in 1960. So I just wanted to highlight that when we address these problems, they're pretty wicked big problems. This has to do with climate change, increased rain, and those sorts of things in our country. All right. This is Lake Erie. This polygon, this map is Lake Erie. So this is the western part of Lake Erie. Here's some of the Lake Erie islands. Toledo would be right there. That's where the Maumee River is, Toledo. So this is the western basin. This is the central basin of Lake Erie, and then the eastern part is chopped off from these maps. I bring this up for you because it shows you how big these blooms were. So red colors means very big, green, nasty, thick bloom. The blues and greens mean a light bloom, and black means there's no bloom there. And what I want to show you is that every year is a little bit different, but some of these are pretty darn intense in how big they are. Okay? Let me get past that. So why? Why do we see these blooms in this western basin, especially right around Toledo? See that little dot right there where it's almost always red? Here's why. This is called a watershed. Okay, you've probably learned about this earlier. So this is the land that ultimately will collect the rain and funnel it into the western side of Lake Erie. Again, Toledo, that is the mouth of the Maumee River, and this is the watershed. So any rain that falls down in this area, rain or snow, will eventually make it into these rivers. So the Maumee and the St. Joe's and the St. Mary's and all the Auglays and all of those will eventually make it into Lake Erie. This map is showing you reds and yellows and greens and whites and browns. I'm going to tell you what land use makes up those colors. Seeing how much brown is in here, what do you think, based on your drive across this part of the state, that represents? You, sir. Good guess. Brown is cultivated crops. Okay? So in everything that's shaded brown, that is where we have agriculture. We have producers, farmers out there growing crops. What that means is there is going to be the application of fertilizers, meaning our N, nitrogen, and our P, phosphorus. So what we have is this big basin or watershed that is going to drain into the lake, the western part of Lake Erie, that has excess nutrients on it. Okay? So we have to talk. If we want to slow nitrogen and phosphorus down, we have to address that big portion. Upwards of almost 73% of the land is in crops. Okay, I'm going to skip over this talk or that slide for timing's sake. What I want to show you is we actually know where most of these nutrients are coming from. Okay, the first one, and it's got some acronyms in here, we have seen 75% reduction in phosphorus coming from wastewater treatment plants. So remember when that lake caught on fire, that river caught on fire? We actually went into our wastewater treatment plants, those facilities that take all the water from our houses and from our streets and from our parking lots and cleans it so the nitrogen and phosphorus isn't in there. The Clean Water Act in the 70s made them clean that water more and more and more. So if you go to the end of the Maumee, so right here, only 9% of the phosphorus at that river comes from wastewater treatment plants, which is good because before it was much more than that. So we know that's where some of the phosphorus is coming from. Who knows what a CSO is? Anybody heard that phrase before? It's a tough one. I didn't think we'd have it in this group. CSO stands for Combined Sewer Overflow. What this means, this is all the water that comes from our houses and from our streets goes into one pipe. And when you get a lot of rainfall, all the water in that pipe is too much for these wastewater treatment plants to clean, so they actually discharge raw sewage, raw untreated water into our rivers and streams. For a long time, a lot of people thought that's where all of our P was coming from. We have done studies at Ohio State and at other universities to show that's not actually the case. Only about 1% of the phosphorus at that Maumee River is coming from here. The next thing was we looked at septic systems. So if you live out in the middle of the country and in rural areas, you don't send your wastewater to these wastewater treatment plants. It sits in septic tanks. We have actually paid researchers, funded science to go out and figure out how much of that phosphorus at the end of the river is coming from septic systems, and it's only about 4%. The next thing we looked at is a bunch of people said, I know what the problem is. It's our lawns. Our parents go out there all the time and put fertilizer on our lawn to grow these great green grasses, and that's where the phosphorus is coming from. So we studied that, and we actually have stopped putting phosphorus in our fertilizers for our lawns. So this isn't a source of that phosphorus anymore. And then a lot of people said, oh, no, I know what the problem is. It's the phosphorus already in the lake. So at the bottom of the lake, a bunch of nitrogen and phosphorus is sitting there, and every time there's a storm event, it moves from the bottom to the top and causes these algal blooms. We studied that internal loading, so that movement of the phosphorus from the bottom of the lake to the top, and only about 3 to 7% of the phosphorus comes from there. So if we did our quick math, 9 plus 1 plus 4 plus 3 or 7, we only know where about 20-ish% of the phosphorus is coming from. So based on that map of how much the land is or what the land is being used for, and this data, we know that most of the nutrients are coming from farms. Okay? Now, I'm saying that not to blame farmers, right? We know that we need farmers. We need the wheat. We need the corn. We need the soybeans to drive our economy. So what we are trying to do is say, farmers, you can use those nutrients, please do, to do your business, but we've got to use them in a way that they don't leave our fields. Let me get through this again for time's sake. So I want to talk to you about this phosphorus and what it looks like. I'm going to show you some more graphs, but I saw people raise your hand. You love science, so we're going to keep going this route. This is phosphorus. So if I went to the Maumee River, right here again, and took a water sample, this is going to be the total amount of phosphorus in that water. I can actually break this down into different things. I can run it through a filter to catch all the water that has dissolved phosphorus. This would be like if you put sugar in a drink and you stirred it. You would taste the sweetness, but you wouldn't be able to chew on the sugar granules. It would be dissolved. But some of that phosphorus is on sediment. It's on dirt. So total phosphorus is both dissolved, where it goes through a filter, and some of it is what's called particulate, and it gets caught on a filter. I'm going to show you on the next couple slides how much of this is in the lake and how much of this is in the lake. So these are your last figures, I think, if I remember back to my presentation. This is where all this nutrients are coming from. Okay, so first, this is that particulate. So if I ran water through a filter, what gets stuck on that filter? So this is going to be the amount, just think of it as how much, and this is the years through time. Here you go. Every dot represents that particulate phosphorus, the phosphorus attached to those sediment particles. Okay? And this black line represents the average of that. What you can see is we're seeing some progress. The numbers were coming down. This is our goal. This is our target. If we hit this number here, the blooms go away. So we're seeing some progress, but it seems to have stabilized a little bit. We think a lot of this dropped off because we started doing something called conservation tillage. So we stopped plowing our fields and kind of leaving them as is before we plant a new seed. I'm going to show you dissolved phosphorus next. So same thing, the amount is here on this vertical axis, or what's called the y-axis, and the date is on the x. So if we plot this, this is where we want to be. The purple dots are each year since the early 70s to roughly present day. And what you can see is we made great progress in the 80s. Things stabilized, but things have gotten worse. And this is what we're trying to work on as scientists. Most of this was because of the Clean Water Act. Remember, we went out to our wastewater treatment plants and we stopped that phosphorus from leaving the wastewater treatment plants. So let's figure out how we're going to do this, right? I'm going to pitch to you 3 different ways, and a lot of these will relate to you personally, but also relate to the farmers that live on the landscape. So the first one is if we get to that reduction, the 40% reduction, we want to be right here, 3 ways, or I call it 3 buckets to get to the solution. One is called 4R stewardship, and I'll define this on the next page for all of us. One is looking at old phosphorus that's already out there in the fields. And the last one is looking at water management. Remember the rain? 11% more in the Great Lakes is coming down, and we got to slow that rain from leaving our fields. Okay? So here's that 4R stewardship. Because of the science we're doing, a lot of it happening at The Ohio State University, is telling farmers they need to do this. We call it the 4 R's because it's right source, right time, right rate, and right place. So this is what our farmers are trying to do right now to solve this problem. Right source means do they buy their fertilizer or do they use manure? Right time means they shouldn't apply it before it rains. Right? Don't go put fertilizer out on your field before it rains because what's going to happen to that fertilizer? It's going to wash right away. Okay? Also, we're telling them not to do it in the winter. So if they put fertilizer on top of frozen ground, what happens in the spring to that frozen ground? It melts, and what happens to the fertilizer that was on top of that frozen ground? Washes away. Glad you guys are all engaged here and paying attention. So right time, right rate, that means we know how much phosphorus corn needs to grow. If you already have that in your soil, should you buy more and add it? No, right? So we're teaching farmers how much to apply based on what's already there. And the last one is the right place. A lot of farmers will go out there with nutrients and spray it on top of the field. If it's just sitting on top of the field, what happens when it rains? Washes away. So what we're telling our farmers to do is actually inject it, to shoot it into the ground so that when it rains, it stays put. So this is what we're telling our farmers. Here's the problem with science sometimes. It's easy for the logic that you just used to say, do this, and your problems will go away. But it's easier said than done. That darn weather. If I'm a farmer, and this is how many days I can be out in my field, if you tell me I can't apply it on frozen ground, then this is how much time I have to be on my field. If you tell me I can't apply the fertilizer before it rains, then this is how much time I have to be out in my field. So the science makes sense, but for the farmer, that's pretty stressful. They don't know when they can get out there and put that nutrient down. Requires many people to be at the table. This thing right here, right place, this is injecting that fertilizer into the soil. Well, we need engineers to design that piece of equipment. And sadly, we're seeing that that piece of equipment doesn't always work the way we wish it did. We need to have conversations and relationships. So if I'm doing one of these things as a farmer, I hope I'm talking to my neighbors to make sure I'm sharing what I've learned. So the people that help you manage your farm, the people that sell you equipment, these people need to be talking about the successes and the cool things that work and don't work. And this isn't always the case. And the last one is we require what are called incentive programs. If I'm a farmer, buying this piece of equipment in here probably cost me $250,000 to buy that tool that injects those fertilizers into the ground. You can tell me it's going to work, but are you going to give me the $250,000 to do it? Okay? So I will tell you we're directionally correct. All of these things are the right things to be doing. Using regular versus manure, when you put it on there, how much you put on, and putting it under the ground. We know all the science says that this is the right thing to be doing, but it's all the behavior things that kind of get in the way. I'm going to skip over this for time's sake. I want to show you this map. This is my map that shows you old phosphorus. So this idea of it's not the phosphorus that you put on in the fall or the spring before you grow your crop. It's stuff that's already out there in your field. And so what we've seen from farmers is that when they don't put any fertilizer down, we still see tons of nutrients leaving their field. So I put this up to remind me of this story. 2018 would be what's called a normal year. So these are satellites going out and measuring the color of the soil. So being brown in May, so these two panels are May. This is, again, that's Toledo. This is the Maumee River, okay? So they can look through satellites and see, yeah, there's a lot of brown out there in May because the crops haven't started growing. But in June, 2018 starts to get green, 2019 doesn't. In July, real green, slightly green, so on and so forth. I show you this because in 2019, why did it stay brown for so long? It's because it rained so much, okay? And with that rain, it meant the farmers couldn't plant their crops, okay? So they didn't go out there and actually put crops in there. Many of them didn't apply fertilizer. Only half of them actually put fertilizer out on the field. And only 15% of them put manure out on the field. So a lot less manure put down. Right time, right rate, all the things we asked those farmers to do, we still saw a bloom in this year. It's because it didn't matter how much nutrients they put down following the 4 R's, there was so much old phosphorus out there that the bloom still happened. Okay? I do want to show you some good news. Remember I said right rate, we're telling farmers not to apply fertilizer if they don't have to? This blue line shows how much fertilizer is bought. And you can see since 2017, our farmers are buying less and less fertilizer, which means the phosphorus that's already in their soil, that is being drawn down, meaning that because they're not applying fertilizer, the crops are stealing phosphorus that was already there. And so we're seeing all this great drawdown or suck down of the phosphorus that's already there. So I want to kind of end here a little bit talking about how science has helped make these decisions. So I'm fortunate enough that we get money from the state of Ohio to fund a harmful algal bloom research initiative. So this is just the cover of a report. But basically I want to show you all the names. The science that we fund, the projects that we fund, 114 projects so far, are driven by what the Department of Natural Resources wants, what the Environmental Protection Agency wants, what agriculture wants, and what the Department of Health wants. So going back to my very first slide, we don't care about science for science sake. We are only doing research, 114 projects, that are answering questions for our state agencies. Okay? These are a table of all the projects. So this is what they want to know. They want to know how that bloom behaves. Why does it start growing when it grows? Why does it die when it dies? Why does it produce toxins on some days and not on other days? So a lot of the research we're doing is to understand how the bloom behaves. We need to treat that water because it produces toxins. So a lot of the research that we've done is just to say, when that water comes into a facility and we clean it up to send it to your house to drink, how do we know it's safe for you to drink? The other thing is, what is the risk to human health? So if you go swimming on that beach that has those blooms, what's going to happen to you? So we fund some of that research. And then last, we want to know why those nutrients leave. Okay, so the right rate, right time, right source, all of that stuff, that is all driven by science questions that we asked through this work. These are the specific things the agencies are asking us. So the Department of Natural Resources wants to know how to build wetlands. Agriculture wants to know, how do we use manure? How do we adapt to climate change? How do we get farmers to do these things on their field that they're not comfortable doing? I'll skip that one. Ohio EPA and the Department of Health want to make sure that the water that we provide to people that live in those cities and along the lake is healthy and safe to drink. Okay? And so we've got some great things going on. These are what farmers are being paid to do. So in our state, farmers can apply for money from our state governments to do all of these things. Figure out how many nutrients I have to add. That's the right rate. Here's subsurface placement of phosphorus. So this is putting it underground, not laying it on the top. Here is how you handle your water on your field. The state is also having us go out and build wetlands. And so in our backyards, we're building 170 wetlands to date to help trap these nutrients that are coming down these rivers and leaving these farm fields. Okay? So there's a bunch of reports out here, and I give them to your teachers and to some of the folks you work with, but it can tell you all this science that is really informing the decisions that we do on the landscape. Okay? Last thing I'm going to leave you with, and then I'm opening it up for questions because we want to get some engagement from all of you. So this is some of the decisions our farmers can make. It's a very small table, so I'm just going to show you where I'm going to talk about. Everything listed here are buffers. So these are things we put at the edge of a farmer's field to stop nutrients from leaving. This is cover crops. So what do you plant on that field when there isn't corn there to keep the nutrients from moving? Here is sediment. How do we slow you losing your topsoil? And all this means in this column, and you can't see it from where you're at, this is how many acres we could probably do that on. So this says cover crops, you could probably 74% of the acres of land that are out there can put cover crops down. But the last column is how much are we actually doing? And so I'm going to zoom in on this table. So here we go. This is nutrient management. This is asking a farmer the right rate. We want you to know how much phosphorus is in your field, and based on that, then we want you to change how much you put on your field. If you already have enough, don't buy fertilizer, don't put it down. If you don't have enough, then go buy the fertilizer. You can see that 77% of the farmers could do that, or 70% of the acres, technically. Or this subsurface placement or manure, so this is putting stuff underneath the ground, we think that 74% of the acres could do that also. Sadly, current adoption rates aren't at that number. So we only have about 60% of our farmers that are actually doing right rate, when 78% could. Injecting the fertilizer into the soil, only 30% of our farmers are doing that, but we know that 74% could. So what we have to do, and it's not the scientists anymore, right? The scientists told them, do this stuff here. But the reason why they're not is because there are people that live there. And those people aren't doing it maybe because they don't understand how to do it. They can't afford to do it. So these are the sorts of things where science can give you the solutions, but communication, management by our state agencies, and even federal and state laws can change these percentages. So we talk to our farmers. So these are the different things they could do. These are the different things they could do. Cover crops, right rate, all those sorts of things. When we ask these farmers, some of the things they tell us is the rules we give them on why to do it don't make sense. Or they don't trust the scientists. They don't trust the institutional things. Or commodity markets, it's too expensive. I can't sell my corn for enough money to make money to do what you're telling me to do. So what I want to kind of leave you with on this slide, I think it goes to the question slide next, is that science can show you the path. It can show you how to behave in the watershed. It can show you how you manage the watershed. It can even help you pass laws to protect the watershed. But if you don't talk to the people and see what makes sense to them or what barriers are there for them, you can't move the needle. You can't solve this harmful algal bloom issue. So with that, I don't want to play this video. If we have time after the questions maybe die down, we'll go into this video. But I'm going to open it up for questions for all of you. What you don't understand or you have questions about phosphorus and nitrogen. But also, I do a lot of work on Lake Erie that isn't in the harmful algal bloom nitrogen space. So I'm happy to take any questions you might have. Don't be shy. Please. Why isn't what one now? Good. So the question is, why isn't manure used more than commercial fertilizers? In my opinion, there's a stigma around using manure. So if you live on a farm and people grab manure and move it and apply it, it has a tendency to have a smell associated with it. So that's one, right? Yeah, but I want to hear what you think about it. I love it. So she's saying, yeah, the smell is horrible, but think about it. You're producing all these manure from the dairy cattle or from the meat cattle or from the hogs, and so why not use it? It's this idea of regenerative ag, taking that nutrients and just bringing it back into the cycle again. And so we are advocating for the use of manure. The problem with manure is you only have certain amounts at a certain time. The manure, oftentimes, the nutrients is such a small part, most of that manure is water. And so you have to haul that manure long distances in a big tanker truck and things like that. So you're right. If you talk to many of the scientists, we would prefer to use manure on our field. Because if you go to the store and buy something, it's just phosphorus. I'm going to the store, I'm going to buy phosphorus fertilizer, I'm going to put it on there. When you use manure, it has phosphorus, it has nitrogen, it has carbon, it has all these great organic things. So for us, in the Maumee Basin, one of the solutions is to use manure. But you just brought up kind of the point I'm trying to drive home here. There are people out there that don't like the stink, don't want to pay to haul it, and so there are just temporary, in my opinion, and I hope in yours, roadblocks right now that we have to move towards. But that's the momentum that I think a lot of people in the academic community are suggesting we do. That's a great question. Thank you. Please. So the question is, to get a lot of the things I pointed out here, subsurface placement, variable rate technology, even putting things like wetlands, building a wetland to stop your nutrients from leaving, it costs money. And the reason is, for your example, for like subsurface placement, so injecting that fertilizer into the soil. A farmer won't make more crop, grow more crop, whether he puts it on the surface or whether he puts it into the bottom. So his money, his paycheck, his revenue stays the same, but he had to spend $250,000 to buy that piece of equipment. So you hit the nail on the head. We have to incentivize or pay these farmers to do it. The problem is some of those farmers are a little hesitant to get into that money space, to take that money from these groups. Plus, that toolbar I just described as you buy this $250,000 piece of equipment and it just works off the shelf. It's a learning curve. They're going to make mistakes with that piece of equipment, and a lot of those farmers aren't comfortable with those risks associated with that. Does anybody have you heard of the word farm insurance or crop insurance? People heard of that? Some, a little bit, good. So some farmers can buy insurance on their crops, right? And so what that means is if there's a drought year or too wet of a year and they don't grow enough crop, they can actually get paid for what they would have grown in previous years. Not usually exactly what they would make, it's usually a reduced rate. So there's a lot of people, business owners, that live in the community that say, that's not fair. Why are we paying farmers when they have a bad year? Where if I own a shop that sells stuffed animals, if I have a bad year, I don't have a stuffed animal insurance to be able to pay me for those bad years. Now, I'm going to tell you that crop insurance means more than that to a farmer, because food, crops we grow, is of national security concern. We need to have enough crops produced in this country to maintain this population, but also to have an export and support other countries. How many stuffed animals you sell in a store isn't of national security. But it brings up that other issue. If you're going to incentivize, if you're going to give farmers to do something, part of the population is going to be like, that's stupid. Why are we paying them to do something that they should just do? That should be their responsibility. And so I'm coming back to your question saying, not everybody's happy with paying farmers to do things. They feel like that burden or that should fall on that person's lap. But it comes back again, I love both these questions. It comes back to the people living in the community, all of you. If you can take one thing away from this is know that, yeah, farmers are part of the problem. Their land is part of the problem. But the reason why they're not jumping in to be the full solution is because the solution's hard. It's going to take investment from the federal government, state government. It's going to have to take people living in the community to just suck it up. You're going to have poop smell outside your house for 3 days. And so the science problems we face sometimes are easy to answer. It's deploying that science so that people can understand it and appreciate it. I'm stressing to you, talk to your neighbors, talk to your friends, figure out why they do what they do and why they don't do certain things. Yeah, please. That's a great question. So he's talking about those CSOs, so the combined sewer overflows. So not all cities have them. Okay, so newer cities will have pipes that take the stuff from your house that has poo and pee and dirty dishes and all that kind of stuff, and then they have a separate pipe that collects water off the roads in the parking lot. So both of those will come into that plant, and they'll treat both of them. But when you have a heavy, heavy rain event, do you pee and poop more? No. So the plant will keep treating that bad water, but that massive amount of water coming off your streets and parking lots, they just let that pass by. So a two-pipe system is the way to go because you don't necessarily have to treat water coming off a street or a parking lot because it's not as harmful to the body as not treating sewage. So the best solution is to go from a one-pipe to a two-pipe. Some people suggest you just need to increase the size of the plant or build a second plant. Those plants cost a lot of money. And is it raining really heavy every day, or are these kind of fluke events? More of a fluke event. And so people are saying it doesn't make money sense to build two plants when you're only going to use one of them occasionally. And so what we're trying to do is figure out how do we separate that one pipe system into two pipes. I'll tell you what they do in Cleveland. When they have heavy storm events and those wastewater treatment plants can't take all the water, they pump it underground into huge pipes. They treat all the water coming from your houses, the polluted, nasty water, and when the rain stops, all the stuff they've been storing underneath Cleveland gets pumped into that facility and they treat it later. So all they're doing is just holding it and storing it until they have the ability to treat it later. But to do that in Cleveland, it costs $3 billion with a B to build those pipes underneath the city. It's a lot of money. Is there another question out there? Please. Good. So the question is about glaciers, and when those glaciers melt, is that meltwater nutrient-rich or nutrient-poor? There will be some nutrients in them just because it can get caught in sediment and settle and get trapped, but not much at all. So those glaciers are pretty clear water, clean water. And they're actually, if you read up on it, I encourage you to, and I'm not an expert in this, when we have these glacier melts or the iceberg melts, they're also not salt water. That's fresh water. And so when you melt those glaciers, it actually has the potential to dilute how salty the ocean water is. That salt then changes the density of water, and it can change global circulations of water based on density of that water. It is a crazy unknown that our scientists are working hard to figure out, like how many glaciers can we melt and ice caps can we melt before we change a lot of that global ocean circulation patterns. It's pretty intense. Yeah, please, sir. There have been people that have talked about taking big tanker ships up, loading them with ice, and then taking those tankers to some of the desert locations, for example, in Africa, in India. So there are people that do it. Usually what pauses that decision is money. To build a big ship, to go chop up ice, put it on a boat, and haul it to another country is more expensive than people are willing to pay for the water. A lot of those countries are doing what are called desalinization plants. So they're pumping in ocean water, stripping out the salt, and then giving people fresh water. Also very expensive, but it's cheaper than hauling icebergs from the Arctic Circle. Good question. These are such great inquisitive questions. I love this. Let's do one more, and then we'll turn it over to the leaders of the program to send you next places. This is amazing. So she's asking about why are we not composting? There's a tremendous amount of food waste in this country. We don't like to see blemishes on our oranges or our bananas or tomatoes, and so we throw them away. We need to fine-tune and make that process more cost-effective. I work with a couple farmers that are just north of here that do that. If they have a restaurant that has a bunch of food waste, they'll take it and compost it. But you have to have somebody that's willing to create a facility, store it. Just like if you have a composter in your backyard, you got to kind of turn that composter and mix it up. So he goes out every day with a big front end loader, a tractor, and flips those piles. Guess who's not happy with him downwind? So you got a smell and a stench associated with it. So those ideas, you're hitting the nail on the head. Using biodigesters for that food and producing methane to use for an energy, those are all things that are being studied right now in our academic institutions. Usually the things that breaks it is when it's cost effective enough to get people to do it. It just takes a lot of money to fine tune these processes. So I know I was done at 12:15. I'm right there. I see some other questions. I wish I could get to them. My email is here. So hopefully your teachers can take this down. I'm happy if you have more questions to log on to a Zoom or team meeting and meet you virtually in your classroom. You let me know what you need. But I appreciate your attention. Amazing questions. Thank you very much, and enjoy the rest of your day.